Hello, everyone. Thanks for coming to this talk. My name is Kunal, and the title of my talk is A Fixed Time Convergent Distributed Algorithm for Strongly Convex Functions in a Time-Varying Network. So this is the outline of my talk. I'll start with some motivation for this work. We'll present a very brief literature review. We'll outline our contributions, and we'll jump to the main results after that, and we'll present one simulation scenario. So distributed optimization, why do we care about it? So for optimization problems with large data sets, we can use data parallelism as allowed by distributed framework, and in economic dispatch type of problems where we want to handle privacy concerns, such as if the individual nodes do not want to share their private objective functions, then that is again allowed in a distributed framework, which is not so much allowed in a centralized framework. And there are various applications of distributed optimization, particularly in large-scale machine learning problems. In this paper, we talk about continuous time algorithms because that enables elegant proofs using the Lyapunov theory. And we leverage something called as fixed time convergence theory, which allows the solutions of the dynamical system to converge to the optimal point within a fixed amount of time, irrespective of where the dynamical system starts from. So the distributed optimization problem has been solved in particularly in discrete time by this particular group for last 10, 12 years. More recently, utilizing the theory of finite and fixed time stability, a lot of people have started working on continuous time algorithms with finite and fixed time convergent results in the distributed optimization problems. Particularly this work by Chen, which came out in 2018, they propose a fixed time algorithm, but they assume that individual objective functions at each node are strongly convex in themselves. So one of the contributions of this work is relaxing this assumption, where we assume that the complete team objective function, the summation of the individual functions, is strongly convex, but the individual objective functions need not be strongly convex in themselves. Other than that, we allow the communication topologies between those nodes to vary in time, and we present a first order scheme in that we only utilize the gradient information, and we do not need to communicate the Hessians, which would account for communication overload in the overall algorithm. So some preliminaries: consider a nonlinear dynamical system with origin being the equilibrium point. We say that the origin is fixed time stable equilibrium if it is a Lyapunov stable, and there exists a fixed amount of fixed time independent of the initial conditions, such that the trajectories of this nonlinear system converge to the origin within that fixed amount of time t. And the authors of this paper presented this kind of a Lyapunov condition where if there exists a Lyapunov function that satisfies this particular, whose time derivative satisfies this inequality along the trajectories of this dynamical system, then the trajectories converge to the origin within this fixed amount of time, irrespective of where the trajectories start from. So we are going to use this result in designing fixed time converging algorithm in this paper. So first, let's see the problem setup. Consider a communication graph given by this graph G between n nodes, which can be potentially time varying. And the main problem that we consider is here. So we want to minimize this objective function given a summation of fi's such that all the x's come to a consensus value. So this is the typical distributed optimization problem setup. We make some assumptions here, particularly that the solution of this problem exists and is unique, that the graph, while can vary in time, but is always connected and is undirected. Each node communicates their private values of xj's and the gradients evaluated at that particular value xj's with their neighbors. And the Hessian of the summation of these functions is strongly convex. So again, we do not assume that individual functions fi's are strongly convex, but their summation is. And this assumption is very easy to satisfy. Even if one of the functions is strongly convex, then the summation would be strongly convex. So it is a relaxation of the common assumption used in the literature. Then objective for this problem is to consider a dynamical system of this form, x dot is equal to ui, and design a ui for each individual node so that in a distributed fashion, each node reaches the optimal value x star within a fixed amount of time. So first we present a centralized protocol. In the centralized protocol, what it basically means is that all the agents are already at consensus, or that their values are same, that the summation of the gradient of the function or the is known, and each node applies the same dynamics. So under these conditions, if the dynamics that each node is applying is given by this particular equation, which is basically the gradient of the summation of the function, that guarantees that the individual nodes reach the optimal point of the optimization problem. If we use this kind of a dynamical system, then it also guarantees that they do so within a fixed amount of time, irrespective of where they start from. So we are going to use this G star in designing a distributed protocol to achieve the same in a distributed fashion. So in order to implement this in distributed manner, we need an estimate of G star for each agent which we denote as GI, which is given as this particular expression on the right-hand side, where theta I is the solution of this dynamical system, where omega I is given out of this equation, which guarantees that all the individual theta i's come to a consensus within a fixed amount of time. And this hi function guarantees that this consensus value is nothing but the summation of these gradient fi's. So this is what we show in this result, which basically says that if these hi's are close enough, where this rho can be arbitrarily large, but it has to be a finite value. So if these hi's are bounded, or the differences between hi's are bounded, then there exists a gain such that if we apply this control law for the theta I dynamics, then all the theta i's would converge to the same value, or equivalently, all the gi's would converge to the same value. Note that this gi is still not equal to g star, and that is something that we achieve in the next result. So for that, what we also need is that all the xi's are also in consensus. So on top of gi, in the control law for each agent, we include this term ui tilde, which guarantees that all the xi's come to consensus. So the first main result is that if each agent applied this kind of a control law, then not only all the GIs would come to consensus, but all XIs would also come to consensus within this fixed amount of fixed time T1 plus T2, where T1 is the time that is needed for consensus on GIs, and T2 time needed for consensus on XIs. So utilizing these steps, we can achieve fixed time distributed optimization in this particular fashion. So first, we do fixed time parameter estimation, and that we achieve consensus over theta I within this time T1. Then we do distributed consensus within a fixed time, so we achieve consensus over xi in time T1 plus T2. And then we use this centralized protocol because all the global information are known by now, so that we can reach the optimal value within this fixed amount of time T1 plus T2 plus T3. And this is what this result statement says, that if each agent applies the design control law, then within this fixed amount of time, they would reach the optimal value of the distributed optimization problem. And the corollary here says that even if the communication topology varies in time, but at each time instance, it remains connected and undirected, then also the same result is going to hold. So next, we demonstrate the result via one example of support vector machine. So The typical SVM problem is given by this, where we want to minimize the summation of these functions uh, in a where in a centralized manner, what we would have is we would have these 500 points that we using which we would need to find this separating hyperplane that separates these labeled data points. In a distributed instance here, we consider that these 500 data points are distributed within 5 agents, so that each agent has 100 data points, which are uh, randomly chosen from these distributed points around the line x is equal to y. And the objective is to find this xi that is basically the separating hyperplane between these labeled data points. So this figure shows the convergence of the summation of the gradients, and it can be noted that the superlinear convergence plotted on the log scale shows that the convergence is achieved within fixed amount of time, and for different initial conditions, we observe that the time of convergence is less than equal to 3 seconds here, and the estimated time or rather the theoretical bound was 10 seconds. So the algorithm reaches the optimal solution in a time much less than the theoretical predicted time. So in conclusion, we presented a novel algorithm to solve distributed optimization problem within a fixed amount of time. We also incorporated time varying communication topology, and future work includes solving the same problem with potentially private convex constraints. So if each node has their own convex constraints that they do not want to share with other agents, as well as the gains, the P, Q, and gammas that we use in the algorithms, if these gains vary between agents and they are privates and the agents do not share that information, then also the the solution could be found in fixed time. So that is the part of our future work. With that, I would like to acknowledge the support of our sponsors, and I'm ready to take any questions if you have.